In this lecture, we are going to talk about rehashing, cuckoo hashing, as well as Cichelli's algorithm. This lecture officially concludes chapter 10. We are going to move on to the next chapter next week. So, you know what hashing is at this point in time, and you know that collisions can be a real problem. They become especially problematic when you start to run out of the space in the hash table. So let's say you have a hash table of a size 100 and let's say 90% of your table is filled. So 90 slots have been filled, only 10 empty slots are available. Surely generating a hash that takes you exactly to those 10 empty slots would be pretty hard, and you might spend a lot of time figuring out collision resolution, trying to decide where to put your 10 remaining items such that no clashes occur. So the more full your table is, the harder it becomes to add new entries to the table. And that is exactly the point where you should actually consider something known as rehashing. So if you see that 90% of your time, whenever you generate a hash, you get a collision, it's definitely time to consider actually creating a larger table. So one thing we perhaps did not explicitly discuss before, hash tables are extremely efficient as far as access is concerned because you calculate the hash and you can go there straight away, but this time efficiency might actually come at a cost. You might have to pay with memory efficiency for it. So for your hash table to remain extremely efficient and easy to insert to, it should always be just a little bit oversized. You want to have enough empty slots so that it's easy enough to resolve whatever collisions occur. So, like I've said, if you realize that collisions are just unbearable, the easiest solution is to simply create a larger table and rehash all the values from the old small table into the new large table. The cost of the operation is going to be obviously O of n, so you will use as many operations to copy the values over as the number of values that you are storing in your small table. If you want to rehash your values, your keys, from a smaller hash table to a larger hash table, you can actually use the same hash function if you want, just make sure that you mod it by a different size of t. Or if you feel like your previous hash function was somehow suboptimal, this is also a good time to maybe consider a different hash function. How do you decide how much larger should the new table be? Well, if you are really struggling to fit things into your current table, then I guess the easiest is just to double the size. But then remember, if you double the size, you will end up with an even number. And as we have discussed before, prime numbers are definitely a better choice for a hash table size, just because they typically give you a better spread of hash values when you mod by the size. So what we typically do is we take the size of the old table, we multiply it by 2, and then we find the prime number which is the closest to that double size. And here is just a simple example. I think the idea is quite trivial. I'm sure you guys get it. We have the original hash table that you can see was getting kind of full. After inserting 23, we will only have 2 slots left, and that is exactly the point, that is exactly the part where inserting new items might become problematic, because there are only 2 available slots, and what are the chances of you hitting exactly 4 or 5? The hash function for this table was just the division hash. In other words, you simply mod by the size of the table. Then I create a larger table. I double my size 7 by 2. I get 14. 14 is obviously not a prime number, so I'm going to find the closest prime number, which happens to be 17, and then I'm actually going to use the same hash function, just this division hash, where I simply mod by the size of the table. But of course, because the size of the table is different now, I will actually get a different spread of values. And here I managed to hash everything without clashes, and I still have plenty of empty space for whatever new values come my way. So that's rehashing in a nutshell. quite a simple concept. In the last lecture, we have discussed a number of different collision resolution algorithms, but you might felt kind of unsatisfied at the end of the lecture because all of them had some problems. Linear probing would cause clusters, quadratic probing would cause some special kind of clusters. It's almost like no matter what we tried, everything seemed kind of suboptimal, and clashes yielded these long chains of operations where you had to iterate through multiple potential positions of where a key could be. And that is indeed the case. If there are lots of collisions in your table, your hash table might become extremely inefficient. And that is why research is actually still ongoing. And in 2001, which is, well, I guess not that recent, but it's recent enough, at least this algorithm was proposed in the 21st century, the cuckoo hashing algorithm was suggested. And it's basically just another collision resolution algorithm, but it comes with an interesting twist. First of all, it gives extremely good efficiency guarantees. So our lookup time, in other words, time to find the key, is guaranteed to be constant. So even if there are collisions, there is still a limited number of lookups, of checks, of hash calculations that you are going to perform. Specifically, it's exactly two. You will either check once or you will check twice. And after your two checks, you will either find the key or you won't. And the reason for it is, in case of cuckoo hashing, we are in fact going to not use a single hash table, but we will use a combination of two hash tables that kind of go hand in hand. Each hash table will have its own hash function associated with it. So if I want to store my values in a hash table and I want to apply cuckoo hashing, I should basically immediately, before I even start entering values, double my hash table, create a hash table and create its clone. And then my first table, the first array, will have a simple hash function of k mod 11. It can be anything that strikes your fancy. And the second hash table must have some different kind of hash. And in my case, we will first divide the key by 11, and then that value is going to be also modded by 11, by the size of the table. So both hashes are quite easy to compute. So how does cuckoo hashing work? What are we going to do with these two tables? As I have already mentioned, every single key can now be in either table 1 or table 2, naturally. Thus, what we are going to do is we are going to get our keys, and if you look at the table here, the keys are in this left column, and then the second column in my blue table, second column is already the hashes for the first table already calculated for you, and the third column in this left hand side table, the third column is h prime, so this is my secondary hash, and I've also already calculated all the hash values. So I have a set of keys, and for every single key I can calculate two different hashes. So essentially the idea is, if the first hash doesn't work, then you should probably try the second hash. Let's see how this works out in practice. We start with 20. So far both hash tables are empty, so we're going to use the first hash, h of k, which is 9. And 20 is just going to go there. Obviously, currently there are no clashes. Then we have 50, and for 50, its first hash, h of k, is 6. So 50 is just going to go to 6. Next up we have 53, and unluckily its first hash is actually exactly the same as 20. It's also 9. It's already competing for that place. So it didn't take us long, we already ran into collisions. So what are we going to do? And this is where the cuckoo idea comes in. So what we are going to do is, we are not going to send 53 to the second table with its second hash. Instead, we will give 53 some agency. 53 is new in this world, it has just gotten its hash of 9, and it believes that it deserves to be in that place. So what 53 is going to do is, it's going to behave exactly like the chick of a cuckoo. I'm sure you all know how cuckoo birds work. They basically lay their eggs in other birds' nests, and then the cuckoo hatchlings essentially kick the original children of the bird out of the nest. So 53 is going to behave exactly that. It's going to behave like a complete bastard. It will kick 20 out of its nest. It will kick 20 out of its spot at 9 so that 53 can take it, because 53 is now the cuckoo's hatchling. Where is 20 going to go though? Well, remember, every single key has 2 hashes, and if 20 is kicked out of its place at 9, it will look its secondary hash up, which is 1, and it will take that position in the second table. So 20 is exiled to the second table, and it goes to position 1, and 53, the cuckoo hatchling, occupies position 9. Next up we have 75. It just looks like there is a lot of competition for position 9. Now 53 has just placed itself there, but we have a new kid on the block, 75. His first hash is also 9, so 75 is now going to kick 53 out of the nest. 53 has to go somewhere else. Where can it go? Well, the second table is the only place, so 53 will take its second hash, which is 4, and that's where 53 is going to end up. And 75 takes its place. Next up we have 100. For the key 100, its first hash is 1 and it's not taken, so that's quite easy. Then we have 67, and 67 is competing with 100 for position 1. So once again, 67 is going to kick 100 out of the cell, and 100 will have to go for its secondary hash, which is 9, and it will take that place 9 in the second table, and 67 takes its place. 105 is going to go for position 6, which once again happens to be occupied. So what are we going to do? We're going to kick 50 out of the nest. Where is 50 going to go? 50 is going to go to position 4. And this suits 105. 105 doesn't care where 50 goes. But as you can see, we have a bit of a problem. 50 was exiled from position 6. And when it goes to its second option, position 4, it realizes that that place is actually also taken by 53. So what are we going to do? Well, the same rule always applies. If you arrive at the destination and you realize it's taken, you just kick out whoever is currently sitting there. So 50 is going to kick 53 out of the nest and take its place. Because 53 only has 2 options, it's either 4 or it's 9, it's going to go back to 9. So 53 is sitting at 9, and remember 75 kicked 53 out of the nest. Now 53 is clearly back for vengeance. It's back and it is going to kick 75 out. So 75 has to go. 75 has a second option, 6, and it happens to not be occupied in the second table. So 75 settles for that. And 53 restores itself in the position 9. So as you can see, in this case, we wanted to simply place 105, but we actually had to do a couple of iterations to make sure that everybody is placed without clashes. Next up we have 3, which just happily settles in location 3, no clashes. Then we have 36, which once again competes for that position. So 36 is going to kick 3 out. 3 is going to go to position 0 in the second table because that's its second option, and 36 will just take its place in position 3. Why is this algorithm good? Well, you might take some time ping-ponging around the 2 tables until everybody is settled, but once everyone is settled, you know that if you do not find 20 at position 9 in the first table, all you have to do is check the second table at position 1. Every single key is either in the first table or in the second table. There is no probing involved. You either settle in one or you settle in the other, and that's just that. In other words, lookup is minimum of 1 steps and maximum of 2 steps, which is obviously very efficient. This lack of clustering and probing is pretty great. There is, however, a slight problem. You did see how my values were kicking each other out for quite some time just to let 105 settle in a specific spot. Well, it turns out you might actually get an infinite loop as a byproduct of this ping pong. You might have 4 values that just kick each other out in this iterative fashion, and none of them can actually settle. So to solve this in practice, we typically set some kind of a maximum number of iterations, maximum number of kicking somebody else out, and if you see that you are taking more than some preset max number of iterations, you know that your hash tables are probably just too full, and it's time to rehash both of those tables. In other words, double them in size, make sure there is more space, and then just repeat the process to copy all the values over from your original two tables to the new two tables, which are larger in size. Okay, so this is just a smart algorithm for collision resolution. Yeah, you should know this for the test. Finally, I have promised that we are going to talk about perfect hash functions and how do you design something that is indeed perfect and also minimal. So just a quick reminder, a perfect hash function is simply a hash function that assigns a unique hash code to every key such that there are no clashes, no collisions. So this is an example of a perfect hash just because we don't have any competition, we don't have any collisions. Now, an even better hash is not just a perfect hash, but a minimal perfect hash. A minimal perfect hash is a perfect hash where there are no empty spaces left in your hash table. So if you have 4 inputs, your hash table size will be 4. You will uniquely place every single key and you will not have a single empty unused slot in your hash table. And obviously something like this is ideal because in this case you have memory efficiency as well as time efficiency. Best of both. Why do we not always go for a minimal perfect hash? Well, basically because it's too hard. As we have discussed in a previous lecture, hash function takes this infinite input space of all possible names, all possible student numbers, all possible telephone numbers, whatever the case might be, and it tries to fit this infinite, unbounded input space to a hash table of a very restricted size. So clearly trying to fit infinity into something finite will never work ideally, will never work perfectly because you don't really know what's coming, therefore you can't prepare for any eventuality. Thus, just because you can't foresee any possible input, you typically cannot design that perfect hash that will guarantee no clashes. However, what if there was a scenario where we did actually know exactly what data was coming? Let's say we were perhaps designing a hash table to store all the different city names in the country. The number of cities is limited. The city names are known beforehand, right? You can look it up. And new cities don't just pop out in the middle of nowhere. So let's say you're trying to hash all the different provinces of the country into a hash table. Again, there is a limited number of provinces. You know exactly what they're called, so there is some determinism. Your input space is no longer unlimited. Well, it turns out that if you do know the input space, if your input space is predefined, if it's not infinite, then, and only then, you can actually go ahead and design your own perfect hash function that is not only perfect, but also completely minimal and waste no space. And that is exactly the next algorithm that we are going to discuss in this lecture. The algorithm is known as the Cichelli's algorithm because it was introduced by the computer scientist by the surname of Cichelli. I think he was Italian. To me that sounds pretty Italian, but you're welcome to Google it in case you're curious. Okay, so the Cichelli's algorithm is actually designed specifically for text, specifically for strings. And if you have a predefined set of strings, then this algorithm essentially gives you the steps to design a perfect minimal hash function. Like I said on the previous slide, this perfect minimal hashing makes sense when you have a limited set of items, right? And cities are a good example, or provinces in the country are a good example. So let's go with cities. Let's go with just a couple of major South African cities and try to create a perfect hash for them. Because I have exactly 4 cities, I obviously want to have a hash table of size 4. I do not want any unnecessary space. I do not want to waste any memory. So let's suppose we are reinventing Google Maps, or maybe we are creating our own proprietary software that essentially needs to store various types of information about the various cities. So we're creating this database. And of course, we want to be able to access every single city and its profile very, very quickly. If you want the speed, hash tables are the way to go. We also know that every single city has a unique name, right? You won't have two Pretorias or two Johannesburgs. It's either one or the other. And because the city names are unique, they actually make pretty good keys, even as strings. And then the greatest thing about cities is that their number is predetermined. We know exactly what cities they are, we know exactly how many they are. So we can plan for this. And so we shall. So here is the Cichelli's hash function that we are going to design. It's actually extremely simple. It has 3 components, and then at the end of the day you mod it by the size of the table. The size of the table is going to be determined by the number of inputs. In this example we have 4 inputs, so t is going to be equal to 4. Length s is simply the length of the string. First letter of s and last letter of s are basically numbers that we decide that we assign to the various unique characters that can occur in the names in the strings. So length s is predetermined by just the length of your string. You can't change that. However, first letter and last letter are 2 parameters that you can actually pick and choose. And the whole idea of the algorithm is to try various combinations of values, of numbers, for the different characters that are used in your string, such that eventually you find a hash function that uniquely hashes everybody without flashes. So we're going to play around with different combinations of numbers for the first and the last characters. And that will allow us to create a perfect hash. Let's see how this works. Before we start playing around with different values, we actually have to consider something. We need to consider the order in which these strings should be hashed. And it turns out that it actually pays to look at the frequency in which the various characters occur. So let's go through all the words, and for every single word see how many times a certain character occurs. So Pretoria starts with a P, so that gives us a frequency of 1 for P, and it ends with an A. So for A we also have a frequency of 1. Johannesburg starts with a J and ends with a G. Durban starts with a D and ends with an N. Cape Town starts with a C and ends with an N. So both Durban and Cape Town end with an N. Therefore the frequency of N in my alphabet here is 2. I have seen 2 N's overall. So these are the total frequencies. Generally our letters are pretty unique. The only character that actually repeats is N. Both Durban and Cape Town end in that character. Now we're going to calculate cumulative frequencies for all the different strings by simply summing the frequency of the first character of each string with the frequency of its last character. And because Durban and Cape Town are the 2 words that actually share the letter N as the final character of the word, they will have higher frequency than Pretoria and Johannesburg. So now that we've calculated the frequency, as you can see, we will sort our strings in terms of the frequencies from the highest to the lowest. And why this is done is we want to obviously hash our words, hash our strings in a particular order, and it turns out that the letters, the words that share the most letters, that have the highest frequency letters involved, typically result in the most clashes, so it's better to place them first. Okay, so we have sorted our list of strings and we have created our hash table on the right hand side. It's right here, as you can see, it has exactly 4 rows. We don't want to waste any space whatsoever. So let's then go ahead and place our words into our table. We do this by removing the first word from the list, of course. Let's start with Durban. And now we have to figure out what its hash value is. To do that computation of length of the word plus first character plus last character, we need to decide what values do we actually assign to the first character of Durban and the last character of Durban. So we have to give values to D as well as to N. And because we are computer scientists, we are probably going to do this with a for loop. Let's just say we try the various integers and we are going to start at 0. So because we don't know any better, let's set D to 0. And same goes for N. 0 is a number. Why start with a random number? Rather start at the beginning. Start with 0, maybe 0 will work. Now that we have assigned values to D and N, to the first and last character, we can calculate the hash. It's quite easy. It's just the length of the word Durban, which is obviously 6 characters, plus the value assigned to D, plus the value assigned to N. Both of those are 0. So we have 6 mod 4, which gives us 2. And now we are going to try and place the word. We will first check if that particular hash that we've generated is taken. If it's not taken, we're going to use it, and then we're going to recursively try to hash the next word in our sequence of words. Otherwise, if you realize there is a clash, the place is already taken, then you obviously have to go back to your choice of values for D and N and try different values. Well, luckily for Durban, he's the first one to arrive, table is empty, everything is up for grabs, so Durban just ends up in position 2, and that's the end of it. To the next word, which is Cape Town. Always take the next one from the top of the list. What should we decide for Cape Town? Well, we have to assign some value for C. What about the value for N? Should we assign some value for N? Well, actually, Durban already decided the value for N, and because Durban is recursively calling this algorithm on Cape Town actually doesn't have the right to change the value of N. The value of N, whatever we choose, should be shared by Durban and Cape Town. So if N is 0, decided by Durban, the same value of 0 must be used by Cape Town. So we can only assign value for C, and now we can calculate the hash. We take the length. In this case, I calculate the space in between Cape and Town also as an extra character. So the length of the word is 9. The values for C and N are both zeros, and this gives me the hash of 1. That's where Cape Town ends up. Next up, we have Pretoria. P and A do not have values here, so let's give values to P and A. Once again, they're just zeros. If zeros work, don't worry about making them different. What do you guys see? What is exactly happening? I'm sure you're noticing that I'm essentially hashing my strings based on their length alone. So in this particular example, the length happens to be a unique enough attribute to actually allow me to create perfect hashing. And if length is all you need, why not take it? If something simple works, just do it. Okay, so for Pretoria we have 8 modded by 4, which is going to give us 0, and that's great. It's not actually taken yet. So far our all zeros are totally working out. Pretoria. Now we're going to place the very last word, which is Johannesburg. Let's see where that guy ends up. Okay, so we have J and we have G, and we set them both to 0 because so far this worked for us just fine. And now we try to calculate the hash. 12 mod 4, oops, we finally get a clash. We get a 0, and we already have Pretoria in that spot, so Johannesburg can't just go ahead and place itself. It got a 0, but we know the only available position is actually position 3. So what are we going to do? Well, if you remember the algorithm, if your first try didn't work, what you should do is play around with different values for the first and the last character. So in the beginning, we will try the combination of J equal to 0 and the various values for G. So we will alter the last character first. Since G of 0 did not work, we are going to try G equal to 1. And that will give us the hash of 1, which is also taken. It's taken by Cape Town. No big deal. Let's try another value for G. Let's try G of 2. 12 plus 2 is going to give you 14, and if you mod that by 4, it will give you 2, which is also taken. It's taken by Durban. So question is, how many different values for g should we actually try? Should we just keep going into infinity until we find something that works? In practice, we say that is not a good idea. We usually do not want to just limitlessly increment the value indefinitely. We typically say, for efficiency's sake, set some maximum value, maximum number of iterations for how many values you can try. And this maximum value is typically chosen as the size of the table divided by 2. Because in my case, size of the table is 4. 4 divided by 2 would give me 2. So I will say the maximum number of iterations for every single individual character is 2. So now we have iterated twice, right? We've tried to alter the value of g twice, and that did not really take us far enough. We are still stuck with a clash, with a collision. What are we going to do? Well, remember, g is just one attribute that we can alter. We can also alter the value of j. So we have to backtrack a little and say, okay, for j of 0, none of the values of g worked. Let's now try to set j to 1, and with j of 1, try once again different values of g. G of 0 we know is not going to work, it will take us to 1. And we try g of 1, that gives us 12 plus 2, 14, once again it takes us to 2, which is taken. And now finally we try a j of 1 and a g of 2, and this gives us 12 plus 1 plus 2, giving you 15. 15 mod 4 is going to be 3, and 3 is actually the last available spot on the table, and that is exactly where Johannesburg can go. Alright, we have discovered the minimal perfect hash for this set of strings. It's just the length of the string plus the value of its first character plus the value of its last character modded by the size of the table. And the values that we ended up with are shown in the little table right here. They are mostly zeros. The only exceptions are j and g, because we had to fiddle a little bit with Johannesburg, but by just fiddling slightly, we didn't actually increment so long. This didn't take too long, and we have managed to place everybody inside of our table. Great, so we have successfully implemented Cichelli's algorithm on a small set of strings. Let's now look at the pseudocode in a little bit more detail. So we are going to create this recursive function assign hash, and we are going to give it a list of words. Just recapping what you've seen on the previous slide, we will always start by removing whatever the top word on the list is. And that for that word, we will try to obviously place it inside of the hash table. And to place it inside of the hash table, we'll have to try and assign values to its first and last character such that no clashes occur. Now, this is very important. I do specify here as a comment next to my two for loops, you can only assign a value to the first character if it has not been assigned yet by a previous recursive step. The same goes for the last value. You can only assign a value to it if it has not been assigned by some previous word. So just like we saw with Durban and Cape Town, they had to share a value for n. And this generally applies to any Cichelli's application. If you have a character and that character is shared by multiple words, then all the words have to share the value assigned to that character. The value assigned should work out for them all. You can't have one value for n for one city and another value for n for another city, because that would mess up your calculation when you're trying to actually look up the words in the table. So that's very important. And next up, I have already told you max is typically calculated as the size of the table, or number of words, which is the same in this case, divided by 2. Just to make it more efficient, to make sure you don't just indefinitely iterate, into infinity. Alright, so once you've chosen the values for your first character and last character, or maybe you've just taken the values already assigned by previous words, you can compute the hash for this particular word. Then you have to check if that hash is taken or not, if it's occupied or not. If it's not taken, then you're in luck, good for you. put a word into that hash and recursively call the function on the next word in the list. Well, we just execute it on a word list. You can imagine word list as a stack, essentially, where every single time the top of the stack is removed. Note that our assign hash has to return some kind of a Boolean value. It has to give us a success or a failure. So let's say we've successfully placed Durban. Durban is then going to call the recursive function on the rest of the words, and it will only accept that the mission was successful if all the other words that tried to place themselves have all succeeded, and in the end this recursive function call returns a success. So if a success is returned, that's great. You just also return a success, and this particular word will then know that it has successfully placed itself in the table. Otherwise, if you fail to place the word, even by alternating all of this first and last, if you just cannot get to this return statement, return success, if this never happens, if you exit your nested for loop and you're still sitting with a failure, all you can do is put the word back on the list, back on the stack, return a failure, sort of false or something like that, and essentially backtrack. So let's say Durban placed itself, but Cape Town totally failed. It will have to report that back to Durban, so that maybe Durban can think of another way to place itself such that Cape Town is also satisfied. So the recursive nature of this algorithm is extremely important. And we are going to do another example, a slightly more lengthy one, just to help you guys visualize how this recursive process works. Okay, let's do another example of Cichelli's, and this time we will do a lot of recursion. In this case, let's say I am hashing these names into my table. I have exactly 6 names: Anna, Maria, Jane, John, Julia, and Megan. And then, because there are 6 words, I will have a table size of 6. You all know that first of all we calculate the frequencies, and I've already calculated them for you. A is the most common character, clearly. M and J, M has a frequency of 2, J has a frequency of 3, E has a frequency of 1, and finally N has a frequency of 2. So we have a nice spread on the frequencies. We'll now calculate the cumulative frequencies for every word. So it's going to be 8 for Anna, 6 for Maria, 4 for Jane, 5 for John, 7 for Julia, and 4 for Megan. Great. Now that we have the frequencies, we're going to sort our list according to the frequencies from the highest frequency to the lowest frequency, giving us the following list: Anna, Julia, Maria, John, Jane, and Megan. Excellent. We have a list. We can now start hashing. And by that, I simply mean we need to try and assign values to the first and the last characters of all of the words such that no clashes occur. Alright, let's do it. Let's start with Anna. Before we go into hashing, just a quick note. I told you that the max is typically determined by the size of the table. So let's practice what we preach. We take the size of the table 6, we divide it by 2, we get a 3. So clearly my max is 3. I should not do more than 3 iterations on each character before I decide to give up. Okay, now I think we have all the information to start hashing. Let us start hashing. Start with Anna. Anna starts with an A as well as ends with an A. So it only has to choose a single value, just a value for A. And we are going to start with 0 because we always start with a 0. We can now calculate the hash. It's just the length of the name plus the 2 values for the first and the last character, giving us 4 mod 6, giving us 4. And because the table is empty so far, we know there are not going to be any clashes to begin with. Great. Anna has placed itself. Now it's going to recursively execute the same algorithm on Julia and wait for Julia to return a success. What is Julia going to do? Julia is going to choose a value for J, but it cannot actually choose a value for A. It has to use the value that Anna has chosen. So J is stuck with 2 zeros, 1 for J and 1 for A. Length of Julia is 5. 5 plus 0 gives you 5. Mod 6 gives you 5 once again, so Julia ends up in position 5. Also seems to be successful, but let's see. Julia is going to recursively execute the same algorithm on Maria. Again, what can Maria do? It has to choose some values. It already has a value for A, so it simply has to choose a value for M. And as you know, it's going to be 0 because we always start there. Maria ends up with a hash of 5. And that is a problem because Julia is already sitting in that place. So how can we resolve this? Well, what control does Maria have over the values of its first and last character? Can it alter the value of the last character, A? No, it cannot, because Anna has set it 2 recursive steps back, so Maria has no control over A. It can actually only alter the value of M. And that is what we are going to do. We are going to try a different value for M. Let's make it 1 instead of 0. Our new hash is 0, and that place is not taken, so Maria places herself there. And because it has managed to find a place for itself, it's going to recursively call the same function on John. Okay, how much freedom does John have? J is already assigned a value of 0 by Julia, so John doesn't have control over J, but it does have control over N, so N is assigned a value of 0. We'll calculate the hash, which is 4, and we realize that that is a clash. Okay, John cannot play around with the value of J, but it can try a different value for N. Let's try 1. We end up with 5. Sadly 5 is also taken, so that's out of the question. Let's try a different value for N. Let's try an N of 2. We end up with a hash of 0. 4 plus 2 is 6, mod 6 gives you 0. Maria is sitting there, so once again this is a no-go. We try one last time, and I'm telling you it's one last time because you know the max is 3. From the original value, we have now tried 3 different other options. We actually are not allowed to try a 4th option, so this better work. Okay, 4 plus 3 is 7, 7 mod 6 is going to be 1, and 1 is not actually taken, so thankfully John does in fact find a place for himself. That's good. John can now invoke the same function on Jane. As you can see, my recursion is slowly bubbling down. Alright, how much freedom does Jane have? Not much more than John. It can't choose a value for J, it can only choose a value for E. And it will start with a 0. And you probably already see that this will be problematic. Jane has the same length as John, right? It also has a length of 4. So as we go through the various values of E, we will experience the same clashes that John was experiencing when he was trying different values for N. So with the value of 0 we'll clash with Anna, with the value of 1 we'll clash with Julia, with the value of 2 we'll clash with Maria, and finally 1 worked out for John because that was the last space after Maria that he took, but now that he's taken it, Jane is competing for the same spot because she has the same length, so she ends up with a very similar hashing experience, and unfortunately she can't actually place herself there because John is now taken to position 1. We have arrived at the max iteration. We are actually not allowed to try more values for Jane. We can't just set E to 4 because max is 3 and we've reached that value. So Jane is screwed. Jane cannot place herself. The only thing she can do is report a failure back to John. What is going to happen when she reports a failure back to John? John can be like, that's okay, let's see if I can do anything. Maybe I can alter my value of N and place myself elsewhere. But the problem is, John is already sitting on the last available value for N. John also has reached its max on iterations. So once Jane reports a failure, John will have nothing but to concur and also report a failure. So Jane is going to backtrack and place herself back on the stack. John is going to backtrack, place himself back on the stack, and we are actually going to be back with Maria. So remove that value for E, it did not work out. Remove that value for N, John's going to also disappear. It did not work out. We are actually back to Maria. Clearly, we have to move Maria somehow so that both John and Jane can actually find a place for themselves. This is exactly why recursion is important. It allows you to always backtrack to previous words and change your mind about the values that you've assigned to the various letters. Okay, so it's all up to Maria. Maria has already changed its value of m once, but it hasn't reached max yet, so it can try something else. It can try an m of 2, and its new hash is going to be 1. However, I'm not going to work through the whole example here. Let's just quickly do a mind experiment. Imagine that Maria moved from location 0 to location 1. It would basically just move down one step. What would then happen to John? Well, you already know that John will clash with Anna and Julia, and then when he tries a j of 2, it will actually generate a 0 and will take place that Maria used to take. And that's all good and well. But now, once again, instead of Maria in position 0 and John in position 1, we'll have Maria in position 1 and John in position 0. So when Jane comes along, she will clash with Anna, Julia, Maria, as well as John. So once again, this will work for John, but it will not work for Jane. So we will have to backtrack twice, once again, like in the previous example, and we'll have to try yet another value for m in case of Maria, because remember, she still cannot alter the value of a. So this is Maria's last chance. We have 5 plus 3, which is 8. 8 mod 6 is going to give us 2. So if Maria goes to 2, what then? Then we know John will manage to hash itself to 0, and Jane will actually manage to hash itself to 1. They will both have to stretch a little and also go almost up to the max, but regardless, John will have a j of 2 and Jane will have, John will set n to 2 and Jane will set e to 3, and both of them will actually find a place. Let's say we are there. Like I said, just writing every single step can be a little bit time consuming, so I was hoping we can talk through it instead. But this is the result of our efforts. Now, Maria has set m to 3, John has set n to 2, and Jane has set e to 3. And so far so good, we have managed to hash these 5 letters. One more to go. We just have Megan. Megan, don't fail us. And here comes Megan. What is the problem with Megan? Megan starts with an M and it ends with an N. And the thing is, Maria starts with M, John ends with N. In other words, both M and N have already been assigned values by other words. So if I ask you how much freedom does Megan have in terms of where to place herself, the answer is she has no freedom, she has no say in it. It's just the length of the word plus whatever she inherits from Maria and whatever she inherits from John for the M and the N, respectively. So we get 8 plus 2, 10, 10 mod 6 gives us 4, and 4 unfortunately is just one integer over 3. 3 is the only available position. We will only be satisfied if we generate exactly 3. And unfortunately, it's not the case now. Right now, Megan is clashing with Anna. And the worst thing about this is Megan can't do anything about it. Megan can't rehash herself because she has no freedom. She inherits the values for M and N. She's stuck with this hash value. So what do we have to do? We obviously have to backtrack. If Megan is not happy, we'll have to go back to Jane, but Jane doesn't have other options, so she'll have to backtrack all the way to John. And John will then try another value for n, the very last one that it can try. John will place itself in position 1. Well, unfortunately, you can probably see where this is going. This will just place Jane in position 0. So Jane is satisfied. Does this change anything for Megan? Let's see. The new value for Megan is even worse. It's even further than 3. We started with a 4. Now, because John has incremented n further, we actually end up with 5. So Megan used to clash with Anna. Now she clashes with Julia. Once again, Megan is unhappy. And what's going to happen next? Well, Megan will have to backtrack to Jane. But Jane is at wit's end. It can't actually do anything, so it will also backtrack. John will also have to backtrack. In fact, even Maria will have to backtrack because it has also tried all the possible values for m and clearly none of that worked. So we'll backtrack all the way to Julia. All of this work that we put into all of these letters, all of these values were obviously, in vain. We have to try at an earlier stage to resolve this conflict. Okay, we are back to Julia. Nothing else we can do. What can Julia do? Well, Julia does have freedom over J, so we will try different values of J. Julia can move from 5 to 0, and so the process continues. I have not worked out this example to the very end, but I encourage you to push on and see if you can place all the words into the table, because there is enough uniqueness between them. I believe this is a resolvable case, but I think this example illustrates in a very good way that even though Cichelli does give you this promise of the perfect minimal hash, actually getting to the perfect minimal hash is not exactly trivial. So if I ask you what is the problem, I'm sure you will immediately point out that it takes a lot of iterations, it takes a lot of backtracking and back and forth trying. It's a recursive algorithm, and if quite far down the line something goes wrong, you might have to backtrack all the way to the beginning and start something different at the beginning and then go all the way into the end again to discover that something else is broken. So there is a lot of back and forth, and this can actually become kind of problematic. In fact, the complexity is exponential. Note how we worked this example out very easily for the 4 cities, but now that we have 6 names, so we have a larger pool of names, and also there are many clashes between them. Obviously, I cherry-picked this example. We have a lot of similarities between the words. Lots of them have the same length, lots of them start with the same letter or end on the same letter. So it's almost like this particular set of words is asking for trouble, right? And yeah, in the worst case, the complexity of your algorithm is going to be exponential. In the best case, it's going to be just linear, where it takes you exactly 1 step to place every single word. But as you know, exponential is as bad as it gets. And of course, if you get there, if you have to backtrack maximum number of times for every single word, that would be quite a disaster. So the bottom line is, this algorithm is quite smart, it's quite simple and it works, but it quickly becomes infeasible for large sets, especially if your large sets of strings have a lot of similarities, if there is kind of not enough uniqueness in the first, last, and length attributes. In fact, for some sets of strings, this algorithm would always fail. And if I ask you what that condition is, you should easily be able to point out that the algorithm only relies on the first and the last character, and it kind of discards all the characters in the middle of your word. So what if we have Jane and Jade in the same set of words? They both have the same length, they both start with J, they both end with E. So no matter what you do, no matter what tricks you try to perform, Jane and Jade will forever collide. There is nothing Cichelli would be able to do to help you there. So if you find yourself in a situation like that, what would be the solution? Well, obviously, if you find that the first and last characters don't have enough variation, you can always add extra parameters to your function. You can always say, I will take the first 2 characters and the last 2 characters. But remember, the more characters you add, the more different combinations you have to try. So the worse the efficiency becomes in terms of the exponential complexity. It becomes slower and slower and slower. So the bottom line is, Cichelli's algorithm is, I think, an interesting example, but I think this illustrates really, really well how hard it actually is to just algorithmically generate a perfect minimal hash. Alright, thanks a lot for your attention. Make sure you understand this algorithm. You are very likely to have to perform something like this in the test. For test purposes, I will usually try to make it feasible, doable within 5 or 10 minutes or so. But yeah, be prepared to do this in test. Thank you very much.